So, so Ryan and his colleague Cotton did an enormous amount of work to create this structured knowledge graph. But one thing I see with almost every knowledge graph that we work with is that half of the data is in unstructured text, sometimes even more. And in many cases, all the juicy parts, right, are not in the structured data, but actually in the underlying text. So in this database uh, that Ryan created, there's 1.2 million triples, but about 120 million, sorry, 120,000 of these triples had pretty large literals, string literals, right? And a lot of very interesting information is in those literals. And so I did what I think is the future of every knowledge graph that you guys are going to work with in the future is that we take every string in your knowledge graph and put it into a vector store. I'm kind of assuming by now everyone knows what a vector store is, and I'm also assuming that everyone knows what RAG is, right? I don't have to explain that. But basically, one thing, so we take every string, we send it to an LLM like OpenAI or Claude, and well, actually not OpenAI, and we get a vector back, and that is the thing that we call an embedding. So here is an, an example where we say, okay, so we have, this is something I just came up, right? Misuse of process trace, just a single string, right? And I say, in all the strings, in all the 120,000 strings that I have, which strings are the closest to, or semantically the closest to the little string misuse of process trace, right? And use Cyber Ryan as the vector store, right? And on the left-hand side of this magic predicate nearest neighbor, what we get back when we do this query is a URI that points to the embedding, meaning the 1536 floats, uh, the dot product, right, or the cosine distance between a term and the thing you're looking for, and and then the term that we find in the database. So I'm looking here and I say, okay, let's do this, and I find the um, the terms that are the closest with this thing here, and you see here the semantic distance, and you see the embedding. Now, if I click on this embedding, then you see that it's actually related to an object that Ryan showed, right? And this object is a STIX object, and the text is monitor for process being viewed that might inject malicious code into processes via p-trace or process trace, right? Um, so that is the simplest. But in the knowledge graph, there's about 20 classes, and I think about 10 of them have interesting strings. So where do these strings appear, right? So I can actually do the next question, the same question, except now I say, okay, given the embedding that I find links to a thing, and what is the class of the thing, and give me the distinct classes. So do the same query, but now I want to know where the strings that matched came from, right? And I execute this, and I find that there are attack patterns from the KPAC database, there's gist techniques, templates, attack patterns, and then other domain objects, right? And these are kind of abstract types because Ryan did a lot of reasoning on the database, but for now they kind of distract from the fact that there's a few interesting classes, right, where these strings came from that matched this string. So now let's go a little bit deeper, right, and look like where we select. Okay, let me say this. So you do that, you find the embedding with RAG of a nearest neighbor, but sometimes you want to only find a match of a term like this in one particular class, right? And so we know the classes now. So I can say, um, same question again, right? Find the nearest neighbor, cyber them, except only match against things that are a gist technique, right? So now we're getting into the graph reg domain. We still do nearest neighbor, but we want the strings that we get only from a subset of our data. Very, very important to realize that, right? Because otherwise, if you just do RAG over a massive amount of data, then you get answers from many different places. And sometimes that's fantastic because you wanted to find that one string. And sometimes it's completely inappropriate because it was not the thing that you wanted to match with, right? So so here I do this one, right? And now I get only terms that come from the class technique, right? And of course, I could change this into anything that I wanted to, right? So I could do attack patterns, intrusion sets, or what have you, right? Now, by the way, this selector thing, so basically what you see here, you have a SPARQL clause, right? And then here you have a selector, and this thing is complete normal SPARQL queries. You could put anything you want. So here we have another one where you say, well, I want to match this term, right? But I only wanted to do it in intrusion sets where the date is before 2022, right? So you see how very detailed you can tell the system where to look for strings that you're interested in, right? And so I can execute this one, right? And now I get, now by the way, you see here the number 3.1, which is, by the way, if you actually were going to read the texts here, then you see they don't get very close to process trace, right? That's because the numbers are very low. So if I would do min score, let's say 0.5, which for the embedding model I'm using, then I wouldn't even get any information because things about process traces are usually not specified in the intrusion set, but in something like the technique or the weakness, right? So anyway, this is nearest neighbor. And then we have the next thing that we can do, and that is we can actually ask for answers in our RAG system, right? So how this works, is where you can, what's happening here is we have a magic predicate called ask my documents. You ask your question, who is affected by log4j, right? Um, and what it will do, it first does a nearest neighbor, and then based on the nearest neighbor, it will concatenate all the terms that you find together, and then you send the question who's affected by log4j plus the fragments that you found to an LLM, and it will find the answer in your fragments. And that is what LLM Ask My Documents does. Does that make sense, right? Because, well, I hope this is clear. Does anyone need any questions about this part, right?
I have a I have a
Yeah,
I have a comment because you were showing me this earlier. We've been working together, but this is this is cool. I don't need to know how to write these complex SPARQL queries. I don't need to know, the knowledge representation and reasoning components to query the knowledge graph here. I
yeah,
mean, who's affected by log4j? That I didn't need any SPARQL or SQL or any of that.
yeah,
It's just your practitioners can make great use of this.
yeah. Well, so here's another example, right? What are some of the bad actors in Eastern Europe, right? And only look in the intrusion set, right? That's what you do here. So this predicate ask my documents again. You can control where you're going to look for answers, and when I look here, right? What are some of the bad actors? It will find this group here, right? Attacking financial institutions in Eastern Europe. And obviously, I could change it to anything I want, right? So if I want to do it in China, right? Back to that attack, whatever, financial institutions, right? Institutions. And if you wait, and here you see APT19, right? APT19, a Chinese-based threat actors targeted multiple industries, blah, 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 notably impacting investment firms. So that is kind of close to the financial part, right? again. So so now, but what you see here, I'm still kind of writing SPARQL queries, right? Except I'm asking meaningful questions about unstructured text in here. Now let's go to the next part where we do natural language queries, right? So let me just go here and I say natural language to SPARQL, right? And I can ask anything about the structure of the database, just something like how many triples do we have per named graph, right? And I can ask this and it will find it, right? Or if I wanted to do the order by descending count, right? Thus, so, oh, by the way, one of the things for those people here, most people here are interested in cyber security, right? And not so much people interested in knowledge graph. But for the few people that are really interested in knowledge graphs, this when we do something like this, right? Actually, we do two things. One, we had the system create shackle, right, over the entire knowledge graph. So here are all the shackles, the shackle shapes for every class that we have in our database, right? And so every time we do a prompt, we give all the shackle to an LLM, right? And then the other thing we do every time we have a successful query, we can save it to the natural language, save it to an underlying vector store, so that the next time, every time we do a query, we also give you all the successful queries. So here I have also a whole database of queries that were successful, right? That I played with and that I used as example to create the next query that you might have. Right? So anyway, let's get a little bit more into the world of cybersecurity. So, for example, I could say, show me a few intrusion sets, right? And here I get the SPARQL, right, for this. Um, and here I get the answer, right? So again, this is way easier than writing the SPARQL here, right? I could also say, show me, say, 20 intrusion sets, right? 20 intrusion sets. And I don't know. So now it has to think. The previous query was in the database. This one was not in the database, so it had to create it, right? But now I get limit 20. Does it make sense? Or I can do something like, okay, show me intrusion sets that have a STIX creation date before 2022, right? And I run this as a query.
I
Let's
don't
see.
think I don't think I gave in the graph I gave you. I don't think I gave you anything. Well,
Yeah,
there. Oh, it's yeah, the STIX creation date. Correct. Okay.
yeah, yeah. No, here's the DS. Yeah, that's why I asked for. Yeah, yeah, you're right. I mean, this is this is not the date of when the intrusion set because we don't have the information, right? But I just wanted to show the principle of it, right? I mean, I can also say after 2021, right, and run it. And again, this beats writing it by hand, right? I think in 10 years we'll tell our children that in the old days people were really writing SPARQL and SQL queries, right? They can't even imagine that anymore. Okay, so now I can do, okay, show me, say, let's say, show me a few examples of an intrusion set where the description contains the words Korea, right? And I run this. So now it is to figure out where the descriptions actually are, right? And then you see the intrusion set, the name of the uh, the name of the intrusion set. Now, by the way, I didn't tell it to give me the name, right? But it thought it was fairly logical that it also got the name, right? So it kind of
Jan,
decided, yeah.
quick interjection. John DeSanto is asking, I may have missed this, but what is mapping the English to SPARQL? Is that a call to an LLM?
Yeah.
And then you said it's validated through shackle validations.
So first, what we did is we created a shackle for the entire database, and just for completeness, and then I threw out all the OWL class, the OWL intersections and OWL unions, etc. I just only kept the meaningful classes, right? So now I have a set of shackle, and I have a database of successful queries where I have the natural language description of the query and the successful SPARQL. And so now when I do a query, the query will look in the database for the queries that it had done before that looked the closest like the thing I'm typing. So again, it uses the vector store to find queries that looked like the one I'm doing right now, right? As a help and all the shackle, and then I give it to an LLM, and then the LLM will write the SPARQL. Now, the LLM will usually screw up the first time, pardon my language, right? And so it will try multiple times till it finally gets a result, and then it will come back. Or it will give me a list of queries that it couldn't decide, but it will give you an explanation, and then you can edit the query yourself. And then once you are happy, you store the successful example, and then you can use it the next time, right? Does it make sense?
Thank you for explaining, yes.
Yeah. For example, I did something like say Korea or Belgium, right? And this is going to take a little while because this one is not in the well. It has to figure out. Yeah. Oh, I did it right. So you see here, right? So the first time when I tried this, it didn't end. This means in our. So by the way, oh, sorry, I should have mentioned, right? So the LLM, we also tell the LLM about some of our underlying magic predicates, right? So they can use it too. So here it does an FTI match where you say, okay, find or anything that starts with Korea or anything that starts with Belgium in the index all, right? Anyway, I'm amazed how well it does this, right? But anyway, so we found in the previous query, right? Tonto Team and Dust Storm. So just for fun, let's do this, right? Let's do this. Give me the description of the CVEs that the intrusion set dust storm might employ, right? So I wanted to remind you guys that this actually is going to be a very complicated query because this one has to go. Let's take the depiction that Ryan created, right, where we go from an intrusion set to an attack pattern that looks like the one from GIST, right, which then links to KPAC, which links to a weakness, which then links to a problem type, but then to a problem type a problem type in a container, and then this container actually has a description here, right? So it's a whole bunch of joins that it has to figure out. So when I do the query and I run it, right? So it's going to take some time because, right? So, I mean, I want you guys to be very impressed now because the LLM managed to take all the shackle, it takes some examples, right, and created this pretty big query, right, to do. I mean, can you imagine that I asked you to write this query, and of course you could use in GraphR visual query language, right, to kind of do it. But I mean, this is way easier, right?
Well, you've impressed the heck out of me.
Yeah. And of course, this is dust storm, right? So if I could take any of the others, I can say the Tonto team might employ, right? And of course, so it's going to do the same thing, except we're going to do dust storm and probably change that in Tonto team, right? Because that's just a single replacement. But again, I'm doing all the work to send it off to an LLM, right? OpenAI, in this case, right, to get the answer back. And again, here, oh, this is fun. Okay, so here it didn't get it, right? Because why didn't it get it? Intrusion set the STIX. Here it says it couldn't do it. And the reason is the SPARQL naturally fails because the clarification prefix ns this ask returns empty response. Oh, that is very weird. Anyway, I'm not going to do the debugging here, right? But this is the work of the future knowledge engineer, right? To go out, ask all stakeholders for questions that they might want to ask of the knowledge graph. The knowledge engineer will help the system write the queries to get huge training sets. So at some point, it should be completely automatic, if that makes sense. And okay, one more thing that I want to show you, and that is, so we did RAG, right? But we can also do the RAG in NLQ itself, right? So for example, I can type here, using RAG, right? What are the main bad actors in China that are attacking financial institutions using the information in intrusion sets, right? And then if we're lucky, right, it will actually write, well, look here, right? Now, again, I think it's, if you just think of it, right, all the processes involved where it gets the shackle, and in previous examples, it goes back to the LLM and then comes back. But actually, the query that it generated does again a call to the vector store and to the LLM again, right? So it's like layers of AI in here, right? And then it gets.
So I wanted to make a comment here,
Yeah.
Jan, is we have been looking at the reference data
Mm-hmm.
that's available to us from NIST and,
Yeah.
and MITRE and National Vulnerability, all of these different reference data that we've pulled together and harmonized with just cyber.
Yeah.
Now, when an enterprise adds to this knowledge graph the specifics of their enterprise,
Yeah.
like what business sector they're in, what vulnerabilities they just, on this morning's vulnerability scan, I received these 5 vulnerabilities that are on my system.
Yeah.
Understanding that those new facts about the enterprise itself in reference to this reference material that we've been talking about for the last few minutes is extremely powerful because it helps the CISO make decisions. Oh, okay, we have these vulnerabilities, but the impact to my institution is low, or the likelihood of exploitation is low. So I don't need to spend precious resources on those today. It allows for decision making at the next level. But that's when you integrate this information with the information about the specific enterprise. You could start asking these natural language questions. Hey, I've just discovered, show me threat actors that might exploit the CVE I just found on, my report this morning. And they'll be able to get those answers. This is incredibly powerful stuff that you're showing us, Jan. And literally, you've only had this data for a couple of days. So I'm impressed as heck.